All right, so this is CS50, and this is the start of week 2. And you'll recall that over the past couple of weeks, we've been building up. First, initially from scratch, the graphical programming language that we then just last week translated to the equivalent program in C. And of course, there's a lot more syntax now. It's entirely text. But the ideas, recall, were fundamentally the same. The catch is that computers don't understand this. They only understand what language? Yeah, zeros and ones are binary. And so there's a requisite step in order for us to get from this code to binary. And what was that step or that program or process called? Yeah, so compiling. And of course, recall, as you've now experimented with this past week, that to compile a program, you can use clang for C language. And you can just say clang and then the name of the file that you want to compile. And that outputs by default a pretty oddly named program, just a.out, which stands for assembler output. But more on that in just a moment. But recall, too, that you can override that default behavior, and you can actually say output instead a program called hello instead of just a.out. But you can go one step further, and you can actually use make. And make itself is not a compiler. It's a build utility. But in layman's terms, what does it do for us? It compiles it, and it essentially figures out all of those otherwise cryptic-looking command line arguments like -o something and so forth, so that the program is built just the way we want it without our having to remember those seemingly magical incantations. And though that only works for programs as simple as this. In fact, some of you with the most recent problem set might have encountered compilation errors that we actually did not encounter deliberately in class because make was helping us out. In fact, as soon as you enhance a program to actually take user input using CS50's library by including CS50.h, some of you might have realized that all of a sudden the sandbox, and more generally Clang, didn't know what getString was. And frankly, Clang might not even know what a string was. And that's because those two are features of CS50's library that you have to teach Clang about. But it's not enough to teach Clang what they look like, as by including CS50.h. Turns out there's a missing step that make helps us solve, but that you, too, can just solve manually if you want. And by that, I mean this. Instead of compiling a program with just clang, hello.c, when you want to use CS50's library, you actually need to add this additional command line argument, specifically at the end. Can't go in the beginning like -o. And -l stands for link. And this is a way of telling Clang, by the way, when compiling my program, please link in CS50's zeros and ones that we, the staff, wrote some weeks ago and installed in the sandbox for you. So you've got your zeros and ones, and then you've got our zeros and ones, so to speak. And -l CS50 says to link them together. So if you were getting some kind of undefined reference error to getString, or you weren't able to compile a program that just used any of the get functions from CS50's library, odds are this simple change, -l CS50, would have fixed. But of course, this isn't interesting stuff to remember, let alone remembering how to use -o as well, at which point the command gets really tedious to type. So here comes make again. Make automates all of this for us. And in fact, if you henceforth start running make and then pay closer attention to the fairly long line of output that it outputs, you'll actually see mention of -l CS50. You'll see mention of even -lm, which stands for math. So if you're using round, for instance, you might have discovered that round2 also doesn't work out of the box unless you use make itself or this more nuanced approach. So this is all to say that compiling is a bit of a white lie. Like, yes, you've been compiling, and you've been going from source code to machine code. But it turns out that there's been a number of other steps happening for you that we're going to just slap some labels on today. At the end of the day, we're just breaking the abstraction. So compiling is this abstraction from source code to machine code. Let's just kind of zoom in briefly to appreciate what it is that's going on in hopes that it makes the code we're compiling a little more understandable. So step 1 of 4, when it comes to actually compiling a program, is called preprocessing. So recall that this program we just looked at had a couple of includes at the top of the file. These are generally known as preprocessor directives. Not a particularly interesting term, but they're demarcated by the hash at the start of these lines. That's a signal to Clang that these things should be handled first, pre-processed, processed before everything else. And in fact, the reason for this, we did discuss last week. Inside of CS50.h is what, for instance? getString, specifically the declaration of getString. So there's some lines of code, the prototype, if you recall, that one line of code that teaches Clang what the inputs to getString are and what the outputs are, the return type and the arguments, so to speak. And so when you have include CS50.h at the top of the file, what's happening when you first run Clang during this so-called preprocessing step is Clang looks on the hard drive for the file literally called CS50.h. It grabs its contents and essentially finds and replaces this line here. So somewhere in CS50.h is a line like this yellow one here that says getString is a function that returns a string, and it takes as input, the so-called argument, a string that we'll call prompt. Meanwhile, with include standard IO, what's the point of including that? What is declared inside of that file, presumably? Yeah?
This is standard inputs and outputs.
Standard inputs and outputs, and more specifically, what example thereof? What function? Yeah, so printf, the other function we keep using. So inside of standard io.h, somewhere on the sandbox's hard drive, is similarly a line of code that frankly looks a little more cryptic, but we'll come back to this sort of thing down the road that says printf is a function, happens to return an int, but more on that another time, happens to take a char star format, but more on that another time. Indeed, this is one of the reasons we hide this detail early on, because there's some syntax that's just a distraction for now. But that's all that's going on. The sharp include sign is just finding and replacing the contents plus ... a bunch of other things in those files as well. So when we say preprocessing, we just mean that that's getting substituted in so that you don't have to copy and paste this sort of thing manually yourself. So compiling is a word that actually has a well-defined meaning. Once you've preprocessed your code and your code looks essentially like this, unbeknownst to you, then comes the actual compilation step. And this code here gets turned into this code here. Now, this is scary looking. And this is the sort of thing that if you take a class like CS61 at Harvard, or more generally systems programming, so to speak, you might see something like this. This is x86 64-bit assembly instructions. And the only thing interesting about that claim for the moment is that assembly, I kind of alluded to that earlier, assembler output, a.out, there's actually a relationship here. But long story short, these are the lower level instructions that only the CPU, the brain inside your computer, actually understands. Your CPU does not understand C. It doesn't understand Python or C++ or Java or any language with which you might be familiar. It only understands this cryptic looking thing. But frankly, from the looks of it, you might glean that probably not so much fun to program in this. I mean, arguably, it's not that much fun to program yet in C. So this even looks even more cryptic. But that's OK. C and lots of languages are just these abstractions on top of the lower level stuff that the CPUs do actually understand, so that we don't have to worry about it as much. But if we highlight a few terms here, you'll see some familiar things. So main is mentioned in this so-called assembly code. You see mention of getString and printf. So we're not losing information. It's just being presented in really a different language, assembly language. Now, you can glean perhaps from some of the names of these instructions, this is what Intel Inside means. When Intel or any brand of CPU understands instructions, it means things like pushing and moving and subtracting and calling. These are all low-level verbs, functions, if you will, but at the level of the CPU. But for more on that, you can take entire courses. But just to take the hood off of this for today, this is a step that's been happening for us magically, unbeknownst to us, thanks to Clang. So assembling. Now that you've got this cryptic-looking code that we will never see again, we'll never need to output again, what do you do with it? Well, you said earlier that computers only understand zeros and ones. So the third step is actually to convert this assembly language to actual zeros and ones that now look like this. So the assembling step happening unbeknownst to you, every time you run Clang or in turn run make, we're getting zeros and ones out of the assembly code, and we're getting the assembly code out of your C code. But here's the fourth and final step. Recall that we need to link in other people's zeros and ones. If you're using printf, you didn't write that. Someone else created those zeros and ones, the patterns that the computer understands. You didn't create getString. We did. So you need access to those zeros and ones so that your program can use them as well. So linking essentially does this. If you've written a program, for instance, hello.c, and it happens to use a couple of other libraries, files that other people wrote of useful code for you, like CS50.c, which does exist somewhere, and even standard.io.c, which does exist somewhere, or technically standard.io is such a big library, they actually put printf in a file specifically called printf.c. But somewhere in the sandbox's hard drive and all of our Macs and PCs, if they support compiling, are, for instance, files like these. But we've got to convert this to zeros and ones, this, and then somehow combine them. So pictorially, this just looks a bit like this. And this is all happening automatically by Clang. Hello.c, the code you wrote, gets compiled to assembly, which then gets assembled into zeros and ones, so-called machine code or object code. CS50.c, we did this for you before the semester started. Printf was done way before any of us started, decades ago, and looks like this. These are 3 separate files, though, so the linking step literally means link all of these things together and combine the zeros and ones from like 3 at least separate files and just combine them in such a way that now the CPU knows how to use not just your code, but printf and getString and so forth. So last week we introduced compiling as an abstraction, if you will. And this is all that we've really meant this whole time. But now that we've seen what's going on underneath the hood, and we can stipulate that my CPU that looks physically like this, albeit smaller in a laptop or desktop, knows how to deal with all of that. So any questions on these 4 steps: preprocessing, compiling, assembling, linking? But generally now we can just call them compiling, as most people do. Any questions? Yeah?
How does the CPU know that when the printf function is the only part of standard I/O that's there? Is that something that it notices in the preprocessing step?
Not in the preprocessing step. So the question is, how does the computer know that printf is the only function that's there? Essentially, when you're linking in code, only the requisite zeros and ones are typically linked in. Sometimes you get more than you actually need if it's a big library, but that's OK too. Those zeros and ones are just never used by the CPU. Good question. Other questions? Yeah. OK. All right. So now that we know this is possible, let's start to build our way back up, because everyone here probably knows now that when writing in C, which is kind of up here conceptually, like it is not without its hurdles and problems and bugs and mistakes. So let's introduce a few techniques and tools with which you can henceforth, starting this week and beyond, try to troubleshoot those problems yourself rather than just trying to read through the cryptic-looking error messages or reach out for help to another human. Let's see if software can actually answer some of these questions for you. So let me go ahead and do this. Let me go ahead and open up a sandbox here. And I'm going to go ahead and create a new file called buggy0.c, in which I will this time deliberately introduce a bug. I'm going to go ahead and create my function called main, which is, again, is the default, like when green flag is clicked. And I'm going to go ahead and say printf, quote unquote, hello world \n. All right, looks pretty good. I'm going to go ahead and compile buggy0, enter. And of course, I get a bunch of error messages here. Let me zoom in on them. Fortunately, I only have 2. But remember, you have to always scroll up to look at the first, because there might just be an annoying cascading effect from one earlier bug to the later. So buggy0.c, line 5 is what this means, character 5, so like 5 spaces in, implicitly declaring library function printf with ... So you're going to start to see this pretty often if you make this particular mistake or oversight. Implicitly declaring something means you forgot to teach Clang that something exists. And you probably know from experience, perhaps now, what the solution is. What's the first mistake I made here? Yeah, I didn't include the header file, so to speak, for the library. I'm missing at the top of the file include standard.io.h, in which printf is defined. But let's propose that you're not quite sure how to get to that point, and how can we get actually some help with this. Let me actually increase the size of my terminal here. And recall that just a moment ago I ran make buggy0, which yielded the errors that I saw. It turns out that installed in the sandbox is a command that we, the staff, wrote called help50. And this is just a program we wrote that takes as input any error messages that your code or some program has outputted. We kind of look for familiar words and phrases just like a TF would in office hours. And if we recognize some error message, we're going to try to provide either rhetorically or explicitly some advice on how to handle. So if I go ahead and run this command now, notice there's a bit more output. I see exactly the same output in white and green and red as before, but down below is some yellow, which comes specifically from help50. And if I go ahead and zoom in on this, you'll see that the line of output that we recognized is this one, that same one I verbally drew attention to before, buggy0.c, line 5, error, implicitly declaring library function printf, and so forth. So here, without the background highlighting, but still in yellow, is our advice, or a question a TF or CA might ask you in office hours. Well, did you forget to include standard.io.h, in which printf is declared, atop your file? And hopefully, our questions, rhetorical or otherwise, are correct, and that'll get you further along. So let's go ahead and try that advice. So include standard.io.h. Now let me go ahead and go back down here. And if you don't like clutter, you can type clear or hit Control L in the terminal window to keep cleaning it like I do. If you want to go ahead now and run make buggy 0, enter, fewer errors. So that's progress, and not the same. So this one's perhaps a little easier. Reading the line. What line of code is buggy here? Yeah, so this is now still on line 5, it turns out. But for a different reason, I seem to be missing a semicolon. But I could similarly ask help50 for help with that and hope that it recognizes my error. So this, too, should start being your first instinct. If on first glance, you don't really understand what an error message is doing, even though you've scrolled to the very first one, like literally ask this program for help by rerunning the exact same command you just ran, but prefix it with help50 and a space. And that will run help50 for you. Any questions on that process? All right, let's take a look at one other program, for instance, that this time has a different error involved in it. So how about, let me go ahead and whip up a quick program here. I'll call this buggy2.c for consistency with some of the samples we have online for you later. And in this example, I'm going to go ahead and write the correct thing at first, standard.io.h. And then I'm going to have int main void, which just gets my whole program started. And then I'm going to have a loop. And recall from excuse me, Mario or some other program, you might have done something like int I gets 0, I is less than or equal to, let's do this 10 times, and then I plus plus. And all I want to do in this program is print out that value of I, as I can do with the %i placeholder. So simple program, just wanted to count from 0 to 10. So let's go ahead and run buggy2. Or rather, let's not print out, rewind. Let's go ahead and just print out a hash symbol and not spoil the solution this way. So here I go ahead and print out buggy2. My goal is, now I will stipulate, to print out just 10 hash symbols, 1 per line, which is what I want to do here. And now I'm going to go ahead and run /buggy2, and I should see, hopefully, 10 hashes. All right, and I kind of spoiled this a little bit, but what do I instead see? Yeah, I think I see more than I expect. And we can kind of zoom in here and double check. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, 11. 11. Now, some of your eyes might already be darting to what the solution should be. But let's just propose that it's non-obvious. And if it is actually non-obvious, all the better. So how might you go about diagnosing this kind of problem, short of just reaching out and asking a human for help? This is not a problem that help50 can help with, because it's not an error message. Your program is working. It's just not outputting what you wanted it to work. But it's not an error message from the compiler with which help50 can help. So you want to kind of get eyes into what your program is doing. And you want to understand, why are you printing 11 when you really are setting this up from 0 to 10? Well, one of the most common techniques in C or any language, honestly, is to use printf for just other purposes, diagnostic purposes. For instance, there's not much going on in this program, but I'd argue that it would be interesting for me to know, and therefore understand my program, by just let's print out this value of I on each iteration, as by doing the line of code that I earlier did, and just say something literally like I is %i. Like, I'm going to remove this ultimately, because it's going to make my program look a little silly, but it's going to help me understand what's going on. Let me go ahead and recompile buggy2 /buggy2. And this time, I see a lot more output. But if I zoom in, now it's kind of now the computer is essentially helping me understand what's going on. When I is 0, here's one of them. When I is 1, here's another. I is 2, 3, 4, 5, 6, 7, 8, 9. And that looks good. But if we scroll a little further, it feels a little problematic that I can also be 10. So what's logically the bug in this program? Yeah, I used less than or equal to because I kind of confused the paradigm, right? Like, programmers tend to start counting at 0, apparently. But I want to do this 10 times. And in the human world, if I want to do something 10 times, I might count up to and including 10. But you can't have it both ways. You can't start at 0 and end at 10 if you want to do something exactly 10 times. So where there's a couple of possibilities here, how might we fix this? Yeah, so we could certainly change it to less than. What's another correct approach? Yeah, so we could leave this alone and just start counting at 1. And if you're not actually printing the values in your actual program, that might be perfectly reasonable too. It's just not conventional. Like, get comfortable with quickly just counting from 0, because that's just what most everyone does these days. But the technique here is just use printf. Like, when in doubt, literally use printf on this line, on this line, on this line. Anywhere something is interesting maybe going on in your program, just use it to print out the strings that are in your variables, print out the integers that are in your variables, or anything else. And it allows you to kind of see, so to speak, what's going on inside of your program. Printf. All right, one last tool. So it's not uncommon when writing code to maybe get a little sloppy early on, especially when you're not quite familiar with the patterns. And for instance, if I go ahead and do this by deleting a whole bunch of white space, even after fixing this mistake by going from 0 to 10, is this program now correct? If the goal is to print 10 hashes. Yeah, I heard yes. Why is it correct? In what sense? Yeah, exactly. It still works. It prints out the 10 hashes, 1 per line, but it's poorly written in the sense of style. So recall that we tend to evaluate, and the world tends to think about code in at least 3 ways. 1, the correctness. Does it do what it's supposed to do, like print 10 hashes? And yes, it does, because all I did was delete white space. I didn't actually change or break the code after making that fix. 2 is design. Like, how thoughtful, how well written is the code? And frankly, it's kind of hard to write this in too many ways because it's so few lines. But you'll see over time as your programs grow, the teaching fellows and staff can provide you with feedback on the design of your code. But style is relatively easy. And I've been teaching it mostly by way of example, if you will, because I've been very methodically indenting my code and making sure everything kind of looks very pretty, or at least pretty to a trained eye. But this, let's just stipulate, is not pretty. Like, left aligning everything still works, not incorrect, but it's poorly styled. And what would be an argument for not writing code like this and instead writing code the way I did a moment ago, albeit after fixing the bug? Yeah? Yeah.
And move on to the next one, and so you know where everything is.
Exactly. Let me summarize this. It allows you to see more visually what are the individual subroutines or blocks of code doing that are associated with each other, right? Scratch is colorful, and it has shapes like the hugging shape that a lot of the control blocks make to make clear visually to the programmer that this block encompasses others, and therefore this repeats block or this forever block is doing these things again and again and again. That's the role that these curly braces serve, and indentation in this and another context just helps it become more obvious to the programmer what is inside of what and what is happening where. So this is just better written because you can see that the code inside of main is everything that's indented here. The code that's inside the for loop is everything that's indented here. So it's just for us human readers, teaching fellows in the case of the course, or colleagues in the case of the real world. But suppose that you don't quite see these patterns too readily initially. That too is fine. CS50 has on its website what we call a style guide. It's just a summary of what your code should look like when using certain features of C, loops, conditions, variables, functions, and so forth. And it's linked on the course's website. But there's also a tool that you can use when writing your code that'll help you clean it up and make it consistent, not just for the sake of making it consistent with the style guide, but just making your own code readable, more readable. So for instance, if I go ahead and run a command called style50 on this program, buggy2.c, and then hit enter, I'm going to see some output that's colorful. I see my own code in white, and then I see anywhere I should have indented green spaces that are sort of encouraging me, put space, 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 space here, put space, 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 space here, put 8 spaces here, 4 spaces here, and so forth. And then it's reminding me I should add comments as well. This is a short program, doesn't necessarily need a lot of commenting to explain what's going on, but just one / like we saw last week to explain maybe at the top of the file or top the block of the code would make style50 happy as well. So let's do that. Let me go ahead and take its advice and actually indent this with tab, this with tab, this with tab, this with tab, and this once more. And you'll notice that on your keyboard, even though you're hitting tab, it's actually converting it for you, which is very common, to 4 spaces. So you don't have to hit the space bar 4 times. Just get into the habit of using tab. And let me go ahead and write a comment here, print 10 hashes. This way, my colleagues, my teaching fellow, myself in a week don't have to read my own code again and figure out what it's doing. I can read the comment alone per the //. If I run style50 again, now it looks good. It's in accordance with the style guide, and it's just more prettily written. So pretty printed would be a term of art in programming when your code looks good and isn't just correct. Any questions then? Yeah? It wasn't enabled for the first week of the class. It's enabled as of right now and henceforth. Other questions? No? All right, so just to recap then, 3 tools to have in the proverbial toolbox now are help 50 anytime you see an error message that you don't understand, whether it's with make or clang or perhaps something else. Printf, when you've got a logical program, a bug in your program and it's just not working the way it's supposed to or the way the problem set tells you it should. And then style 50, when you want to make sure that it does my code look right in terms of style and is it as readable as possible. And honestly, you'll find us at office hours and the like often encouraging you, hey, before we answer this question, can you please run style 50 on your code? Can you please clean up your code? Because it just makes our lives, too, as other humans, so much easier when we can understand what's going on without having to visually figure out what parentheses and curly braces line up. And so do get into that habit because we'll save you time from having to waste time parsing things visually yourself. All right. So there's not just CPUs in computers. CPUs are the brain, central processing unit, and that's why we keep emphasizing the instructions that computers understand. There's also this, which we saw last time too. This is an example of what type of hardware? RAM, or random access memory. This is the type of memory that laptops, desktops, servers have that is used whenever you run a program or open a file. There's another type of memory called hard drives or solid state drives, which you're probably familiar as a consumer, and that's just where your files are stored permanently. You can, your battery can die, you can pull the plug from your laptop or desktop, and any files saved on a hard drive are persistent. They stay there because of the technology being used to implement that. But RAM is more ephemeral. RAM is powered only by electricity. It's only used when the power is on or the battery is charged. And it's where your files and programs live, effectively when you double click on them and open them. So when you double click on something like Microsoft Word, it is copied from your hard drive long term into this type of memory, because this type of memory, though smaller in capacity, you don't have as many bytes of it, but it is much, 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 much faster. Similarly, when you open a document or you go to a web page, the contents of the file you're seeing are stored in this type of hardware, because even though you don't have terribly many bytes of it, it's just much, 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 much faster. And so this will be thematic in computer science and in hardware. You sort of have lots of cheap, slow stuff, like hard disk space, relatively speaking, and you have a little less of the more expensive but faster stuff, like RAM. And you have just one, usually, CPU, which is the really fast thing that can do 1 billion things per second. But it, too, is more expensive. So there's 4 visible chips on this thing, if you will. And we won't get into the details of how these things work, but let's just zoom in on this one black chip here and focus on it as being representative as some amount of memory. Maybe it's 1 megabyte, 1 million bytes. Maybe it's even 1 gigabyte these days, 1 billion bytes. But this is to say that this chip can be thought of as just having a bunch of bytes in it. So this is not to scale. You have many more bytes than these. But let me propose that you just think of each of these squares here as representing 1 byte. So the very first byte of memory I have access to is here. Next one is here, and so forth. And the fact that they wrap around is just an artist's rendition. These things you can think of just virtually as going left to right, not in any kind of grid. But physically, they look like this. So when you actually create a variable in a program like C, like you need a char. A char tends to be 1 byte or 8 bits. And so that means when you have a variable of type char in a C program, it goes literally, physically, in one of these boxes inside of your computer's RAM. So for instance, it might take up this much space at top left. If you have a bigger type of data, so you have an integer, which tends to be 4 bytes or 32 bits, you might need more than 1 square. So the computer might give you access to 4 squares instead, and you have 32 bits spanning that region of memory. But honestly, I chose those boxes arbitrarily. They could be anywhere in that chip or in any of the other chips. It's up to the computer to just remember where they are for you. You don't need to remember that per se. But if we think about this grid, it turns out this is actually very valuable, that we have chunks of memory, bytes if you will, that are back to back to back to back. And in fact, there's a word for this technique. This is contiguous memory, back to back to back to back to back. And in general, in programming, this is referred to as an array. You might recall from Scratch, if you use this feature, it actually has things called lists, which are exactly that, lists of values, lists of words, lists of strings. An array is just a contiguous chunk of memory such that you can store something here, something here, something here, something here, and so forth. So it turns out an array, this super simple primitive, is actually incredibly powerful. Just being able to store things in my computer's memory back to back to back to back enables so many possibilities, both design-wise, like how well I can write my code, and also how fast I can make my code run. So let me go ahead and take out an example. Let me go ahead and open up, for instance, a new file in a sandbox, and we'll call this scores0. So let me go ahead and close this one, create a new file called scores0.c. And in this file, let's go ahead and write a relatively simple program. Let me go ahead and, as usual, give myself access to some helpful functions, CS50.h and standardio.h. And no need to copy all this down verbatim if you don't like. Everything we'll have or is already on the course's website. Let me start my program as usual with int main void. And then let me write a program, as this program's name implies, that asks the user for 3 scores on recent problem sets, quizzes, whatever, and then kind of creates a very simple chart of them, like a bar chart, to kind of help me visualize how well or how poorly I did on something. So if I want to get an integer, no surprise, we can use the getInt function, and I can just ask the user for their first score. But I should probably do something with this score. And on the left-hand side of this, what do I typically put? Yeah, so int, sure, score 1 equals this, and then my semicolon. So you might not have had many occasions to use ints just yet, but getInt is in the CS50 library. This is the so-called prompt that the human sees. And let me actually fix my space, because I want the human to see the space after the colon. But that's just an aesthetic detail. And then when I get back this value, its return value, just like Aaron last week handed me a piece of paper, so does getInt hand me a virtual piece of paper with a number that I'm going to store in a variable called score1. And now, just to be clear, what has just happened effectively is this. The moment you create a variable of type int, which is 4 bytes, literally, this is what Clang, or more generally, the computer, has done for you. That int that the human typed in is stored literally in 4 contiguous bytes, back to back to back, maybe here, but together. So that's all that's going on when you're actually using C. So let me go back into my code here. And now it's not interesting to plot one score, so let's go ahead and do another. So int score2, getInt, and I'll ask the user for score2, semicolon, and then let's get one more, score3, getInt, call it score3, semicolon. All right, so now let me go ahead and generate like a bar chart of this. I'm going to use what we'll call ASCII art. ASCII, of course, is just text, recall. Very simple text in a computer. And you know what? I can kind of make a bar chart pretty simply by just printing out like a bunch of hashes horizontally. So a short bar will represent a small number, and a long bar will represent a big number. So let me go ahead and say to the user, all right, here's your score 1. I'm going to go ahead then and say for int I gets 0, I is less than score 1. I++. And now if I scroll down and give myself a bit of room here, let me go ahead and implement just a simple print. So go ahead and print out a hash. And then when you're all done with that, print out a new line at the end of that loop. And let's just pause there. Just to recap, I've asked the human for 3 scores. I'm only doing something with one of them at the moment. So in fact, just as a quick check, let me delete those so as to not get ahead of myself. Let me do make score 0, cross my fingers. OK, no errors. Now let me go ahead and do /score 0. And your first score on a p-set this year out of 100 has been, OK, 100. And good job. So it's a really long bar. And if we count those up, hopefully there's actually 100 bars. And if we run it again and say, it didn't go so well, I got 50, that's half as big a bar. So it seems like we're on our way correctness-wise. So now let me go ahead and get the other scores. Well, I had them here a moment ago. So let me go ahead and just, kind of copy paste and change this to 2, change this to 3, change this to 3, this to 3. All right, I know how to print bars clearly. So let me go ahead and do this, and then do this, and then fix the indentation. I don't want to say score 1 everywhere. I want to say score 2, score 2. I mean, you're probably being rubbed the wrong way, that this is both tedious and sloppy. And why? What am I doing poorly now, design-wise?
Copy-pasting code.
Like copy-pasting, almost always bad, right? There's redundancy here, but that's fine. Let's prioritize correctness, at least for now. So let me go ahead and make score 0. All right, no mistakes. /score 0. And the habit. Let me go ahead now and run. OK, we got 100 the first time. We got 50 this. Oh, that's a bug. What did I do there? See, this is what happens when you copy paste. So let's fix this. That should say score 2. So Control-C will quit a program. Make score 0. We'll recreate it. /score 0. Enter. All right, here we go. 100. 50. Let's split the difference. 75. All right, so this is a simple bar chart, horizontally drawn, of each of my 3 scores, where this is 100, this is 50, and this is 75. But there's opportunities for improvement here. So one, it rubbed some folks the wrong way already that we were literally copying and pasting code. So where's one opportunity for improvement here? What should I do instead of copying and pasting that code again and again? What ingredient can you bring? OK, so we could use a loop and actually just do the same thing 3 times. So let's try that. Let me go ahead and do this. So let's go ahead and delete the copy paste I did. And let me go ahead and say, OK, well, for int I gets 0, I less than 3, I plus plus. Let me create a bracket. I can highlight multiple lines and hit tab, and they'll all indent for me, which is convenient. And can I do this now, for instance? Say a little louder.
If you enter a specific, at least as far as I can see, if you enter a specific score, it will be the same.
Yeah, I'm a little worried, as you're noting here. We're using on line 13 here the same variable. So like, so it's good instincts, but I feel like the fact that this program, unlike last week, we're now collecting multiple pieces of data, loops are breaking down for us. Yeah.
You could create a function that basically takes in like an input, like you can have it like
OK.
so like an input of how many scores you want to enter,
OK.
and then I don't know, that would clean up.
Yeah, we can implement another function that factors out some of this functionality. And other thoughts?
Store your scores in an array.
OK, so we could also store our scores in an array. So let's do these in order then, in fact. So loops are wonderful when you want to do something again and again and again. But the whole purpose of a function fundamentally is to factor out common functionality. And there might still be a loop in this solution, but the real fundamental problem with what I was doing a moment ago was I was copying and pasting functionality. Shouldn't need to do that because in both C and Scratch, we had the ability to make our own functions. So let's do that. Let me undo my loop changes here just to get us back to where we were a moment ago. And let me go ahead and instead clean this up a little bit. Let me go ahead and create a new function down here that I'm going to call, say, chart, just to create a chart for myself. And it's going to take as input a score, but I could call this anything I want. It's void as its return type because I don't need it to hand me something back. Like I'm not getting a string from the user. I'm just printing a chart. It's a so-called side effect or output. All right, now I'm going to go ahead and do my loop here. For int I gets 0, I is less than, how many hashes do I want to print if I'm being passed in the user score? Like, is this 3 here?
Score.
The score. So if I'm being handed a number that's 0 to 100, that's what I want to iterate over. If my goal here, ultimately, let me finish this thought, I plus plus is to, inside this loop, print out 1 hash per point in one's total score. And just to keep things clean, I'm going to go ahead and put a new line at the very end of this. But I think now I factored out a good amount of the redundancy. It's not everything, but I've at least now given myself a function called chart. So up here, it looks like I can kind of remove this loop, which is what I factored out. That's almost identical, except the variable name was hard-coded. And I think I could now do chart like this. And then I maybe could do a little copy-paste, if that's OK. Like if maybe I can get away with just doing this, and then say 2, and then say 3, and then say 3, and then say 2. So it's still copy-paste, but it's less, and it looks better. It literally fits on the screen. So it's progress. Not perfect, but progress. Better design, but not perfect. So is this going to compile? I'm going to have errors. Why?
Because essentially it's running the program top down.
OK.
At the very end.
Yeah.
You need to sort of declare a void.
OK, good. So and let me induce the actual error just so we know what problem we're solving. Let me go ahead and sort of innocently go ahead and compile, score 0, hoping all is well. But of course, it's not because of a familiar error up here. So notice implicit declaration of function chart is invalid in C99. So again, implicit declaration of function just tends to mean Clang does not know what you're talking about. And you could run help 50, and it would probably provide you with similar advice. But the gist of this is that chart is not a C function. It doesn't come with C. I wrote it. I just wrote it a little too late. So one solution that we didn't use last week would be, OK, well, if you don't know what chart is, let me just go put it where you'll know about it. And now run make score 0. OK, problem solved. So that fixes it. But we fixed it in a different way last week. And why might we want to stick with last week's approach and not just copy paste my function and put it at the top instead of the bottom? Yeah, I mean, it's kind of a minor concern at the moment because this is a pretty short program. But I'm pushing like the main part of my program, literally called main, farther and farther down. And like the whole point of reading code is to understand what it's doing. So if I open this file and I have to scroll, just looking for the main function, like that's just bad styles. It's just kind of nice, and it's a good human convention. Put the main code, the main function, when green flag clicked equivalent, at the very top. So C does offer us a solution here. You just have to provide it with a little hint. Let me go ahead and cut this from here, put it back down at the bottom here, and then go ahead and copy paste only, or retype only, the value, the value of that first line, which is its so-called prototype. Give Clang enough information so that it knows what arguments the function takes, what its return type is, and what its name is, semicolon. And that's the so-called declaration, and then implement it with the curly braces and all the logic down below. So let's go ahead and run this. And if I scroll up here, we'll see, we'll see make score 0. All right, now we're on our way. Score 0, enter. Score 1 is 100, 50, 75. And now we seem to have some good functionality. But there's still an opportunity, I dare say, for improvement. And I think the fundamental problem is that I'm still copy pasting a little stuff. But I think the fundamental problem is that I don't have the expressiveness to store multiple values unless I, in advance, as the programmer, give them all unique names. Because if I use the same variable for everything, I couldn't collect all 3 variables at the top and then iterate over all 3 at the bottom if I only have 1 variable. So I do need 3 variables, but this doesn't scale very well. And who knows, if I want to take in 5 scores, 10 scores, or more scores, then I'm really copying and pasting excessively. So it turns out, indeed, the answer is an array. So an array, at the end of the day, is just a side effect of storing stuff in memory back to back to back to back. But what's powerful about this reality of memory is the following. I can go ahead here and in, say, a new and more improved version of this program, do this. Let me go ahead and open this one, which I wrote in advance, called scores2.c. And in scores2.c, notice we have the following code. In my main function, I've got a new feature and a new bit of syntax. This line here that I've highlighted says, hey, Clang, give me a variable called scores of type integer, but please give me 3 of them. So the new syntax here is square brackets, and inside of which is the number of variables you want of that type. And you don't have to give them unique names. You literally call them collectively scores. And in English, I deliberately chose a plural to connote as much. This is an array of values, not a single value. What can I do next? Well, here's my for loop. For int I gets 0, I is less than 3, I++. And now I've solved that earlier problem that was proposed. Well, just put it in a loop. Now I can, because now my variables are not called score1, score2, score3, which I literally had to hard code. They're just called scores. And now that they're called scores and I have this square bracket notation, notice what I can do. I can get an int, and I can say, give me score %i, and plug in I plus 1. I didn't want to say 0 because humans don't count from 0 in general. So this is counting from 1, 2, and 3. But the computer is doing this. So scores is a variable. Bracket I, close bracket, says store the ith value there. So ith is just non-English. That means go to bracket 0, bracket 1, bracket 2. So what this effectively means is on the first iteration of this loop, when I equals 0, this looks like this effectively. When I then becomes 1 on the next iteration, then you're doing this. When I becomes 2 on the final iteration, it looks like this. When I becomes 3, well, 3 is not less than 3, and so it doesn't execute again. So by using I inside of these square brackets, am I indexing into an array? To index into an array means go to a specific location, the so-called ith location, but you start counting at 0. Just to make this more real then, if you go back to this picture of your computer's memory, this might therefore be bracket I, bracket 1, bracket 0, bracket 1, bracket 2, bracket 3, bracket 4, bracket 50, or wherever. You can now, using square brackets, get at any of these blocks of memory to store values for you. All right. right, any questions on what we've just done? All right, then on the flip side, we can do the exact same thing. Now when I print my scores, I can similarly iterate from 0 to 3 and then print out the scores by passing to chart the same value, the ith score. Again, the only new syntax here is variable name, square bracket, and then a number like 0, 1, 2, or a variable like I. And then my chart function down here is exactly the same. It has no ID and array isn't even involved because I'm just passing in one score at a time. Now, it turns out there's still one bad design decision in this program. There's still some redundancy, something that I keep typing again and again and again. Do any values jump out at you as repeated? The for loop. OK, so I've got the for loop in multiple places, sure. And what other value seems to be in multiple places? It's subtle. Total number, yeah, 3. Like 3 is in a few places. It's up here. It's when I declare the array and ask myself for 3 scores. It's here when I'm iterating. It's here when I'm iterating. It's not here because this is a different iteration. That's just for the hashes. So ironically, 3 places have I written 3. So what does this mean? Well, suppose next year you take more tests or whatever and you need more scores. You open up your program and, all right, now I've got 5 scores and 5. Oh, oops, see a typo already, 5. Like this kind of pattern where you're typing the same thing again and again, and now the onus is on me, the programmer, to remember to change the same damn value in multiple places, like bad, bad, bad design. You're going to miss one of those values. Your program's going to get more complex. You're going to leave one at 3 and change the other to 5, and like logical errors are eventually going to happen. So how do we solve this? The function's not the solution here because it's not functionality. It's just a value. Well, we could use a variable, but a certain type of variable. These numbers here, 5, 5, 5, or 3, 3, 3, are what humans generally refer to as magic numbers. Like they're numbers, but they're kind of magical because you've just arbitrarily hard-coded them in random places. But a better convention would be, often as a global variable, to do this. Int, let's call it count equals 3. So declare a variable of type int that is the number of things you want, and then type that variable name all throughout your code so that later on, if you ever want to change this program, you change it, whoops, in one place, and you're done after recompiling the program. And actually, I should do a little better than this. It turns out that if you know you have a variable that you're never going to change, because it's not supposed to change, it's supposed to be a constant value. C also has a special keyword called const, where before the data type, you say const int, and then the name, and then the value. And this way, the compiler, Clang, will make sure that you, the human, don't screw up and accidentally try to change the count anywhere else. There's one other thing notable. I also capitalized this whole thing for some reason. Human convention. Anytime you capitalize all of the letters in a variable name, the convention is that that means it's global. That means it's defined way up top, and you can use it anywhere, therefore, because it's outside all curly braces. But it's meant to imply and remind you that this is special. It's not just a so-called local variable inside of a function or inside of a loop or the like. Any questions on this? Yeah?
Scores like down there, why do you have I+1?
Oh, why do I have I+1? Let me run this program real quick. Why do I have I+1 in this line here is the question. So let me go ahead and run make scores 2. Whoops. In my directory, make scores 2, /scores 2, enter. I wanted just the human to see score 1 and score 2 and score 3. I didn't want him or her to see like score 0, score 1, score 2, because it just looks lame to the human. The computer needs to think in terms of zeros. My humans and my users like do not. So just an aesthetic. Other questions? Yeah?
For better style, why don't we just combine the 2 for loops there so the scores inside?
Really good question. So, and I actually thought about this last night when trying to craft this example. Why don't I just combine these 2 for loops? Because they're clearly iterating an identical number of times. Was this a hand or just a stretch? No, stretch. So this is actually deliberate. If I combine these, what would change logically in my program? Yeah? Yeah, so after every human input of a score, I would see that user's chart the row of hashes. Then I'd ask them for another value. They'd see the chart, another value, and they'd see the chart. And that's fine. Like, if that is the design you want, totally acceptable, totally correct. I wanted mine to look a little more traditional with all of the bars together. So I effectively had to postpone printing the hashes. And that's why I did have a little bit of redundancy by getting the user's input here and then iterating again to actually print the user's output as a chart. So just a design decision. Good question. Other questions? All right, so what does this look like? Actually, you know what? I can probably do a little better. Let me open up one final example involving scores and this thing called an array. In scores 4 here, let me go ahead and do this. Now I've changed my chart function to do a little bit more. And you might recall from week 0 and 1, we had the cough function. And we kept enhancing it to do more and more, like putting more and more logic into it. Notice this chart function now takes a second argument, which is kind of interesting. It takes one argument, which is a number, and then the next argument is an array of scores. So long story short, if you want to have a function that takes as input an array, you don't have to know in advance how big that array is. You should not, in fact, put a number in between the square brackets in this context. But the thing is, you do need to know at some point how many items are in the array. If you've programmed in Java, took APCS, Java just gives you .length, if you recall that feature of objects. C does not have this. Arrays do not have an inherent length associated with them. You have to tell everyone who uses your array how long it is. So even though you don't do that syntactically here, you literally just say, I expect an argument called scores that is an array per the square brackets. You have to pass in almost always a second variable that is literally called whatever you want, but is the number of things in that array. Because if the goal of this function is just to iterate over the number of scores that are passed in, and then iterate over the number of points in that score in order to print out the hashes, you need to know this count. So what does this function do? Just to be clear, this iterates over the total number of scores from 0 to count, which is probably 3 or 5 or whatever. This loop here, using j, which is just a convention, instead iterates from 0 to whatever that ith score is. So this is what's convenient. Now I've passed in the array, and I can still get at individual values just by using I, because I'm on my ith iteration here. So you might recall this from Mario, for instance, or any other example in which you had nested loops. It's just very conventional to use I on the outside, j on the inside. But again, the only point here is that you can indeed pass around arrays even as arguments, which we'll see why that's useful before long. Any questions? OK, so this was a lot. But we can do so much more still with arrays. They get even more and more cool. In fact, we'll see in just a bit how arrays have actually been with us since last week. We just didn't quite realize it under the hood. But let's go ahead and take a breather, 5 minutes. We'll come back and dive in. All right, so I know that was a bit of a cliffhanger. Where else could arrays have actually been? But of course, this is how we might depict it pictorially. We've called it an array. And it turns out that last week, when we introduced strings, sequences of characters, are literally just an array by another name. A string is an array of chars. And chars, of course, is another data type. Now, what are the actual implications of this, both in terms of representation, like how a computer is representing information, and then fundamentally, programmatically, what can we do when we know all of our data is so back to back to back or so proximal to one another? Well, it turns out that we can apply this logic in a few different ways. Let me go ahead and open up, for instance, an example here called string 0. So in our code for today, in our source2 folder, let me go ahead and open up string 0. And this example looks like this. Notice that we first, on line 9, get a string from the user. Just say, input, please. We store that value in a string s. And then we say, here comes the output. And notice what I'm doing in the following line. I'm iterating over I from 0 to strlen.c, whatever that is. And then in line 13, I'm printing a character one at a time. But notice the syntax I'm using, which we didn't use last week. If you have a string called s, you can index into a string just like it's an array, because it indeed is underneath the hood. So s bracket I, where I starts at 0 and goes up to whatever this value is just a way of getting character 0, then character 1, then character 2, then character 3. And so the end result is actually going to look like this. Let me go ahead and do make string 0. Whoops, not in the directory. Make string string 0, /string 0, enter. And I'll type in, say, Zamila. And the output now is Z-A-M-Y-L-A. It's a little messy because I don't have a new line here. So let's clean that up because this is unnecessarily sloppy. So let me go ahead and print out a new line. Let me recompile with make string 0, /string 0. Input shall be Zamila, enter. And now Z-A-M-Y-L-A. So why is that happening? Well, if I scroll down on this code, it seems that I am, via this printf line here, just getting the ith character of the name in S, and then printing out one character at a time per the %c, followed by a new line. So you might guess, what is this function here doing? Strlen, slightly abbreviated, but you can perhaps glean what it means. Yeah, so it's actually string length. So it turns out there is a function that comes with C called strlen. And humans back in the day and to this day like to type as few characters when possible. And so strlen is string length. And the way you use it is you just need one more header file. So there's another library, the so-called string library, that gives you string-related functions beyond what CS50's library provides. And so if you include string.h, that gives you access to another function called strlen that if you pass it a variable containing a string, it will pass you back as a return value the total number of characters. So I typed in Z-A-M-Y-L-A, and so that should be returning to me 6, thereby printing out the 6 characters in Zamila's name. Yeah?
For the credit, you said, would this have been useful to get the individual digits to be?
Really good question. In the credit problem of the problem set, would this have been useful? Yes, absolutely. But recall that in the credit p set, we encouraged you to actually take in the number as a long, so as an integral value, which thereby necessitated arithmetic. But yes, if you had instead, in a problem involving credit card numbers, gotten the human's input as a long string of characters and not as an actual number like an int or a long, then yes, you could actually get at those individual characters, would have made things even easier. But deliberate. Yeah?
If you're defining string in CS50, are you redefining it in string?
Really good question. If we're defining string in CS50, are we redefining it in string? No. So string, even though it's named string.h, doesn't actually define something called a string. It just has string-related functions. More on that soon. Yeah?
Edit the individual values of it, or is it read-only?
Really good question. Could you edit the individual values? So short answer, yes. We could absolutely change values, and we'll soon do that in another context. Other questions? All right, so turns out this is correct if my goal is to print out all of the characters in Zamila's name. But it's not the best design. And this one's a little subtle, but this is, again, what we mean by design. And to a question that came up during the break, did we expect everyone to be writing good style and good design last week? Like, no. Up until today, like, we've introduced the notion of correctness in both Scratch and in C last week. But now we're introducing these other axes of quality of code, like design, how well designed it is, and how pretty does it look in the context of style. So expectations are here on out meant to be aligned with those characteristics, but not in the past. So there's a slight inefficiency here. So on the first iteration of this loop, I first initialize I to 0, and then I check if I is less than the length of the string, which hopefully it is if it's Zamila, which is longer than 0. Then I print the ith character. Then I increment I. Then I check this condition. Then I print the ith character. Then I increment I. Then I check this condition, and so forth. We looped through loops last week, and you've used them perhaps by now in problems. What question am I redundantly asking seemingly unnecessarily? I have to check a condition again and again because I is getting incremented. But there's another other question that I don't need to keep asking again just to get the same answer.
What is the length of this string?
Yeah, there's this function call in my loop of strlen.s, which is fine. This is correct. I'm checking the length of the string. But once I type in Zamila, her name is not changing in length. I'm incrementing I, so I'm moving in the string, if you will. But the string itself, Z-A-M-Y-L-A, is not changing. So why am I asking the computer again and again, get me the strlen of s, get me the strlen of s, get me the strlen of s? So I can actually fix this. I can improve the design because that must take some amount of time. Maybe it's fast, but it's still a non-zero amount of time. So you know what I could do? I could do something like this. Int n gets string length of s. And now just do this. This would be better design, because now I'm only asking the question once of the function. I'm remembering or caching, if you will, the answer. And then I'm just using a variable. And just comparing variables is just faster than comparing a variable against a function which has to be called, which has to return a value, which you can then compare. But honestly, it doesn't have to be this verbose. We can actually be a little elegant about this. If you're using a loop, a secret feature of loops is that you can have commas after declaring variables. And you can actually do this and make this even more elegant, if you will, or more confusing looking, depending on your perspective. But this now does the same thing, but declares n inside of the loop, just like I'm declaring I. And it's just a little tighter. It's one fewer lines of code. Any questions then? Good question. In the way I've just done it, cannot reuse this outside of the curly braces. The scope of I and n exists only in this context right now. The other way, yes, I could have used it elsewhere.
What I'm saying is, like, what if you created other loops and you also had another section where you wanted to
Absolutely.
using different letters of the alphabet, you could just use n and not be afraid that it might be set.
Correct. If I want to use the length of s again, absolutely, I can declare the variable, as I did earlier, outside of the loop so as to reuse it. That's totally fine. Yes. And even I exists only inside of this loop. So if I have another loop, I can reuse I, and it's a different I because these variables only exist inside the for loop in which they're declared. So it turns out that these strings don't have anything in them other than character after character after character. And in fact, let me go ahead here and draw a picture of what's actually going on underneath the hood of the computer here. So when I type in Zamila's name, I'm, of course, doing something like Z-A-M-Y-L-A. But where is that actually going? Well, we know now that inside of your computer is RAM or memory. And you can think of it like a grid. And honestly, I can think of this whole screen as just being in a different orientation, a grid of memory. So for instance, maybe we can divide it into rows and columns like this, not necessarily to scale. And it's more rows and columns. So on the screen here, I'm just dividing things into the individual bytes of memory that we saw a moment ago. And so indeed, underneath the hood of the computer is this layout of memory. The compiler has somehow figured out, or the program has somehow figured out where to put the Z and where the A, and then the M and the Y and the L and the A. But the key is that they're all contiguous, back to back to back. But the catch is, if I'm typing other words into my program, or scores into my program, or any data into my program, it's going to end up elsewhere in the computer's memory. So how do you know where Zamila begins and where Zamila ends, so to speak, in memory? Well, the variable called s essentially is here. There's some remembrance in the computer of where s begins. But there's no obvious way to know where Zamila ends unless we ourselves tell the computer. So unbeknownst to us, anytime a computer is storing a string like Z-A-M-Y-L-A, turns out that it's not using 1, 2, 3, 4, 5, 6 characters. It's actually using 7 secretly. It's actually putting a special character of all zeros in the very last byte. Every byte is 8 bits, so it's putting secretly 8 zeros there. Or we can actually draw this more conventionally as \0 is what's called the null character, and it just means all zeros. So the length of the string Zamila is 6, but how many bytes does it apparently take up, just to be clear? So it actually takes up 7. And this is kind of a secret implementation detail that we don't really have to care about, but eventually we will, because if we want to implement certain functionality, we're going to need to know what is actually going on. So for instance, let me go ahead and do this. Let me go ahead and create a program called strlen itself. So this is not a function, but a program called strlen.c. Let me go ahead and include the CS50 library at the top. Let me go ahead and include standard.io.h. Let me go ahead and type out int main void. So all this is same as always. And then let me go ahead and prompt the user for, say, his or her name, like so. And then, you know what? Let me actually this time not just print their name out, because we've done that ad nauseum. Let's just count the number of letters in his or her name. So how could we do that? Well, we could just do this. Int n gets strlen of s, and then say printf, the length of your name is %i. And then we can plug in n, because that's the number we stored the length in. But to use strlen, I have to include what header file? String.h, which is the new one. So string.h. And now if I type this all correctly, make strlen Good. /strlen. Let's try it. Zamila. Enter. OK, the length of her name is 6. But what is strlen doing? Well, strlen is just an abstraction for us that someone else wrote, and it's wonderfully convenient. But you know, we don't strictly need it. I can actually do this myself. If I understand what the computer is doing, I can implement this same functionality myself as follows. I can declare a variable called n and initialize it to 0. And then, you know what? I'm going to go ahead and do this. While s bracket n does not equal all zeros, but you don't write all zeros like this. You literally do this, that \0 to which I referred earlier in single quotes. That just means all zeros in the byte. And now I can go ahead and do n++. If unfamiliar with what this means, remember that this is just n equals n plus 1, but it's just a little more compact to say n++. And then I can print out the name of your n, the length of your name is %i, plugging in n. So why does this work? It's a little funky looking, but this is just demonstrating an understanding of what's going on underneath the proverbial hood. If n is initialized to 0, and I look at s bracket n, well, that's like looking at s bracket 0. And if the string s is Zamila, what is s bracket 0? Z. And then it does not equal \0. It equals z, obviously. So we increment n. So now n is 1. So what is s bracket 1 in Zamila's name? A, and so forth, and we get to Z, A, M, Y, L, A, then all zeros, the so-called null character, or \0. That, of course, does equal \0, so the loop stops, thereby leaving the total count or value of n at what it previously was, which was 6. So that's it. Like, all underneath the hood, all we have is like memory laid out like this, top to bottom, left to right. And yet all of the functionality we've been using for a week now and henceforth just boils down to some relatively simple primitives. And if you understand those primitives, like, you can do anything you want using the computer, both computationally code-wise, but also memory-wise. We can actually see, in fact, some of the stuff we looked at 2 weeks ago as follows. Let me go ahead and open up an example called ASCII 0. Recall that ASCII is the mapping between letters and numbers in a computer. And notice what this program is going to do. Let me go into this folder. Make ASCII 0, /ASCII 0, enter. The string shall be, let's say, Zamila, enter. Well, it turns out that if you actually look up the ASCII codes for Zamila's name, Z is 90, lowercase a is 97, M is 109, and so forth. There are those characters. And actually, we can play the same game we did last week. If I do this again on like hi, there's your 72, and there's your 73. Where is this coming from? Well, now that I know how to manipulate individual strings, notice what I can do. I can get a string from the user, just as we always have. I can iterate over the length of that string, albeit inefficiently, using strlen here. And then notice this new feature today. I can now convert one data type to another. Because a char, a character, is just 8 bits, but presented in the context of characters. Byte is also just 8 bits that you could treat as an integer, a number, right? It's totally context sensitive. If you use Photoshop, if it's a graphic, if you use a text program, it's a message, and so forth. So you can, in code, change the context. So notice here, s bracket I is, of course, the ith character of Zamila's name, so Z or A or M or whatever. But I can convert that ith character to an integer doing what's called casting. You can literally, in parentheses, specify the data type you want to convert one data type to, and then store it in exactly that data type. So s bracket I, convert it to a number, then store it in an actual number variable, so I can print out its value. So C, this is show me the character, show me the letter, as by plugging in the character and then the letter. The character and the number that I've just converted it to. And you don't actually even have to be explicit. This is called explicit casting. Technically, we can do this implicitly too. C, and the computer knows that numbers are characters and characters are number. You don't have to be so pedantic and even do the explicit casting in parentheses. You can just do it implicitly with data types. And honestly, at this point, I don't even need the variable. I can get rid of this. And down here, I can literally just print the same thing twice, but tell printf to print the first is in the context of a character and the second in the context of an int, just treating the exact same bits differently. That's implicit casting. And it just demonstrates what we did in week 0 when we claimed that letters are numbers, and numbers can also be colors, and colors can be images, and so forth. Is this a question?
Would have been useful for credit.
Also, yes, it all comes back to credit. Well, yes, indeed. Other questions? All right, so what else can we actually do with this appreciation? So super simple feature that all of us surely take for granted if we even use it anymore these days. Google Docs, Microsoft Word, and such can like automatically capitalize words for you these days. Even your phone can do it nowadays to just sort of autocorrect your messages. Well, how is that actually working? Well, once you know that a string is just a bunch of characters back to back to back, and you know that these characters have numbers representing them, and like capital A is 65, and lowercase a is 97 apparently, and so forth, like we can leverage these patterns. If I go ahead and open up this other example here called capitalize 0, notice what this program is going to do for me first by running it. Make capitalize 0 dot slash capitalize 0. Let me go ahead and type in Zamila's name just as before, but now it's all capitals. So this is a little extreme. Hopefully your phone is not capitalizing every letter, but you can imagine it capitalizing just the first if you wanted it. So how does this work? Well, let me go ahead and open up this example here. And so what we did, so here I'm getting a string from the user, just as we always do. Then I'm saying after, just to kind of format the output nicely. Here I'm doing a loop pretty efficiently from I equals 0 up to the length of the string. And now notice this neat application of logic. It's a little cryptic, certainly at first glance, but whoops, and now it's gone. And what am I doing exactly with these lines of code? Well, with every iteration of this loop, I'm asking the question, is the ith character of s, so the current character, is it greater than or equal to lowercase a? And is it less than or equal to lowercase z? Put another way, how do you say that more colloquially in English? Is it lowercase? Literally, but this is the more programmatic way of expressing, is it lowercase? All right, if it is, go ahead and do this. Now, this is a little funky, but print out a character, specifically the ith character, but subtract from that lowercase letter whatever the difference is between little a and big A. Now, where did that come from? So it turns out, OK, capital A is 65. Lowercase a is 97. So the difference between those is 32. And that's true for B. So capital B is 66, and lowercase b is 98, still 32, and it repeats for the whole alphabet. So I could just do this. If I know that lowercase letters have bigger numbers, like 97, 98, and I know that lowercase numbers have lower letters, like 65, 66, I can just literally subtract off 32 from my lowercase letters. As you point out, it's a lowercase letter, subtract 32, and that gives us what result? The capitalized version. It uppercases things for us. But honestly, this feels a little hackish that, like, OK, yes, I can do the math correctly. But you know what? It's better practice generally to abstract this away. Don't get into the weeds of counting how many characters are away from each other. Math is cheap and easy in the computer. Let it do the math for you by subtracting whatever the value of a is, capital A is, from the value of lowercase a. But we could just write 32. Otherwise, go ahead and just print the character unchanged. So in this case, the A, M, Y, L, A in Zamila's name got uppercased, and everything else, the Z, got left alone, just by understanding what's going on with how the computer's represented. But honestly, God, I don't want to keep writing code like this. Like, I'm never going to get this. I'm new to programming, perhaps. I'm never going to get this sort of sequence of all the cryptic symbols together, and that's OK, because we can actually implement this same program a little more easily, thanks to functions and abstractions that others have written for us. So in this program, turns out I can simplify the questions I'm asking by literally calling a function that says is lower. And there's another one called is upper. And there's bunches of others that just literally are called is something or other. So is lower takes an argument like the ith character of s, and it just returns a bool, true or false. How is it implemented? Well, honestly, if we looked at the code that someone else wrote decades ago for is upper, odds are, or is lower, odds are he or she wrote code that looks almost like this. But we don't need to worry about that level of detail. We can just use his or her function. But how do we do that? Turns out that this function, and you would only know this by having been told or Googling or reading a reference, is in a library called ctype.h. And you need the header file called ctype.h in order to use it. And we'll almost always point you to references and documentation to explain that to you. ToUpper is another feature, right? This math, like, my God, I just want to uppercase a letter. I don't want to really keep thinking about how far apart uppercase letters are from lowercase. Turns out that in the ctype library, there's another function called ToUpper that literally does the exact same thing in the previous program we wrote. And so that too is OK. But you know what? This feels a little verbose it would be nice if I could really tighten this program up. So how does toUpper work? Well, it turns out some of you might be familiar with CS50 reference online, or web-based app that we have that helps you navigate available functions in C. Turns out that all of the data for that application comes from an older command line program that comes in Linux and comes in the sandbox called man for manual. And anytime you type man at the command prompt and then the name of a function you're interested in, if it exists, it will tell you a little something about it. So if I go to toUpper, man toUpper, I get slightly cryptic documentation here. But notice toUpper and some other functions convert uppercase or lowercase. That's the summary. Notice that in the synopsis, the man page, so to speak, is telling me what header file I have to include. Notice that under synopsis, it's also telling me what the signature or prototype is of the function. In other words, the documentation in man, the Linux programmer's manual, is very terse. So it's not going to hold your hand in this black and white format. It's just going to convey, well, implicitly, you better put this atop your file. And by the way, this is how you use the function. Takes an argument called c, returns a value of type int. Why is it int? Let me wave my hands at that. It effectively returns a character for our purposes today. And if we scroll down, OK, description. I don't really want to read all of this. But OK, here we go. If C is a lowercase letter, toUpper returns its uppercase equivalent if an uppercase representation exists in the current locale. That just means if it's punctuation, it's not going to do anything. Otherwise, it returns C. And that's kind of the key detail. If I pass it lowercase a, it's going to give me capital A. But if I pass it capital A, what's it going to give me? Also capital A. It returns the original character C. That's the only detail I cared about. Like when in doubt, like read the manual. And it might be a little cryptic. And this is why CS50 reference takes somewhat cryptic documentation and tries to simplify it into more human-friendly terms. But at the end of the day, these are the authoritative answers. And if I or one of the staff don't know, like we literally pull up the man page or CS50 reference to answer these kinds of questions. Now, what's the implication? I don't need any of this. I can literally get rid of the condition and just let toUpper do all of the legwork. And now my program is so much more compact than the previous versions were, because I've read the documentation, I know what the function does, and I can let toUpper uppercase something or just pass it through unchanged. So again, better design because we're writing fewer lines of code that are just as clear. And so we can now actually tighten things up. Any questions on this particular approach? All right, so we're getting very low level. Now let's make these things more useful, right? Because clearly other people have solved some of these problems for us, as by having these functions and these the C-type library and the string library. What more is there? Well, recall that every time we run clang or even run make, we're typing multiple words at the command prompt. You're typing make hello or make Mario, a second word. Or you're typing clang -o hello, hello.c, like lots of words at the prompt. Well, it turns out that all this time you're using, indeed, command line arguments. But in C, you can write programs that also accept words and numbers when the user runs the program. Think back, after all, when you ran Mario, you did /Mario, enter. You couldn't type any more words at the prompt. When you did credits, you did /credit, enter. No more words at the prompt. You used getString or getLong to get more input, but not at the command line. And it turns out that we can relatively simply in C, but it's a little cryptic at first glance. Let me go ahead and here pull up this signature here, which looks like this. This is the function that we're all used to by now for writing a main function. And up until now, we've said void. Main doesn't take any inputs. And indeed, it just runs. But it turns out if you change your existing programs or future programs, not to say void, but to say int argc string argv. It's a little cryptic at first glance, but what's a recognizable symbol now? Yeah, there's brackets here. So it turns out that every time you write a program, if you don't just say void, you actually enable this feature by writing int argc string argv. You can actually tell Clang, you know what? I want this program to accept one or more words or numbers after the name of the program. So I can do /hello David or /hello Zamila. I don't have to wait for the program to be running to use getString. And just as with the earlier example where you were able to chart an array, main is defined as taking an array called argv for historical reasons, argument vector. Vector means array. Argument vector bracket close bracket just means this contains one or more words. It's each of which is a string. Argc is argument count. So this is the variable that main gets access to that tells it how many arguments, how many strings are actually in argv. So how can we use this in a useful way? Well, let me go ahead here and open up the sandbox. And let me go ahead and create a new file called, say, argv0, argv0.c. Again, argument vector, just list or array of arguments. And let me go ahead and, as usual, include CS50.h, include standard io.h, and then int main, not void, but int argc string argv, open bracket, close bracket. And even if that doesn't come naturally at first, it will eventually. And I'm going to do this. If the number of arguments passed in equals 2, then I'm going to go ahead and do this. Printf hello %s, comma, and here in the past I've typed a variable name, and I now actually have access to a variable. Go ahead and do argv bracket 1. Else, if the user does not type apparently 2 words, let me go ahead and just by default say hello world as we always have. Now what is this doing and how is it doing it? Well, let's quickly run it. So make argv0 /argv0 enter hello world. But if I do hello or the program would be better named if we called it hello, but Zamila, enter hello Zamila. If I change it to David, now I have access to David. If I David Malin, no, it doesn't support that. So what's going on? If you change main in any program or write to take these two arguments, argc and argv, of type string, int, and then an array of strings, argc tells you how many words were typed at the prompt. So if the human typed 2 words, I presume the first word is the name of the program, /argv0. The second word is presumably my name, if he or she is actually providing their name at the prompt. And so I print out argv bracket 1, not 0, because that's the name of the program, but argv bracket 1. Else, down here, if the human doesn't provide just Zamila or just David or just one word more generally, I just print the default hello world. But what's neat about this now is notice that argv is an array of strings. What is a string? It's an array of characters. And so let's introduce one last piece of syntax that gets kind of powerful here. Let me go ahead and do this. Let me go ahead and in a new file here, argv1.c. Let me go ahead and paste this in, close this. Let me go ahead and do this. Rather than do this logical checking, let me do this. For, let's say, for int I gets 0, I is less than argc, I ++, let's go ahead and 1 per line print out every word that the human just typed, just to reinforce that this is indeed what's going on. So argv bracket 0, save, make argv1, enter. And now let's go ahead and run this program, /argv1, David, Malin. OK, you see all 3 words. If we change it to Zamila, we see just those 2 words. If we change it to Zamila Chan, we see those 3 words. So we clearly have access to all of the words in the array. But let's take this one step further. Rather than just print out every word in the string, let's go ahead and do this. For int j gets 0, n equals the string length of the current argument. Like this, j is less than n, j++, j++. Now let me go ahead and print out not the full string, but let me do, let me go ahead and print out this. Not a string, but a character in bracket I, bracket j, like this. All right, so what's going on? 1, this outer loop, and let's comment it, iterate over strings in argv. This inner loop, iterate over chars in argv bracket I. So the outer loop iterates over all of the strings in argv. And the inner loop, using a different variable, starting at 0, iterates over all of the characters in the ith argument, which itself is a string, so we can call string length on it. And then we do this up until n, which is the length of that string, and then we print out each character. So just to be clear, when I run argv1 and correct it, at first glance, why It's implicitly declaring library function strlen. What's almost always the solution when you do this wrong? Yeah, so I forgot this. So include string.h. And help50 would help with that as well. Let's recompile with make argv1. All right, when I run argv1 of, say, Zamila Chan, what am I going to see? Yeah. Is that the right intuition? I'm going to see Zamila Chan, but one character on each line, including the program's name. So in fact, let me scroll this up so it's a little bigger. Enter. OK, it's a little stupid, the program, but it does confirm that using arrays, do I have access not only to the words, but I can kind of have the second dimension. And within each word, I can get at each character within. And we do this, again, just by using not just single square brackets, but double. And again, just break this down into the first principles. What is this first bracket? This is the ith argument, the ith string in the array. And then if you take it further with bracket j, that gives you the jth character inside of this. Now, who cares about any of this kind of functionality? Well, let me scroll back and propose one application here. So recall that CS is really just problem solving. But suppose the problem that you want to solve is to actually pass a secret message in class or send someone a secret for whatever reason. Well, the input to that problem is generally called plain text, a message you want to send to that other person. You ideally want ciphertext to emerge from it, which is enciphered, scrambled, somehow encrypted information so that anyone in the room, like the teacher, can't just grab the note and read what you're sending to your secret crush across the room or in any other context as well. But the problem is that if the message you want to send, say, is our old friend hi with an exclamation point, you could encode it in certain contexts as just 72, 73, 33. And I dare say most classes on campus, if you wrote on a piece of paper 72, 73, 33, passed it through the room, and whatever professor intercepts it, they're not going to know what you're saying anyway. But this is not a good system. This is not a crypto system. Why? It's not secure. What do you think? No?
Yeah, people know the ASCII.
Yeah, anyone has access to this, right? So long as you attend week 1 or 0 of CS50, or you just have general familiarity with ASCII, this is not this is just a code. I mean, ASCII is a system that maps letters to numbers, and anyone else who knows this code obviously knows what your message is because it's not a unique secret to you and the recipient. So that's probably not the best idea. Well, you can be a little more sophisticated. And this is back actually a photograph from World War I of a message that was sent from Germany to Mexico that was encoded in a very similar way. It wasn't using ASCII. The numbers, as you can perhaps glean from the photo, are actually much larger. But in this system, in a militaristic context, there was a code book. So similar in spirit to ASCII, where you have a column of numbers and a column of letters to which they correspond, a code book more generally has numbers and then maybe even letters or whole words that they correspond to, sometimes thousands of them, literally a really big book of codes. And so long as only, in this context, the Germans and the recipients, the Mexicans, had access to that same book, only they could encrypt and decrypt, or rather encode and decode information. Of course, in this very specific context, and you can read more about this in historical texts, this was intercepted, this message, seemingly innocuous, though definitely suspicious, looking with all these numbers, so therefore not innocuous. The British, in this case, actually intercepted it, and thanks to a lot of efforts in cryptanalysis, the Bletchley Park style code breaking, albeit further back, were they able to figure out what those numbers represented in words and actually decode the message. So, and in fact, here's a photograph of some of the words that were translated from one to the other. But more on that in any online or textual references. Turns out in this poem, too, there is a similar code, right? It's apropos of being in Boston here. You might recall this one. Listen, my children, and you shall hear of the midnight ride of Paul Revere. On the 18th of April in 75, hardly a man is now alive who remembers that famous day and year. He said to his friend, if the British march by land or sea, from the town tonight, hang a lantern aloft in the belfry arch of the North Church Tower as a signal light. 1 if by land, and 2 if by sea. And I on the opposite shore will be, ready to ride and spread the alarm, though every Middlesex village and farm, for the country folk to be up and to arm. So it turns out some of that is not actually factually correct, but the 1 if by land and the 2 if by sea code were sort of an example of a one-time code, because if the revolutionaries and the American Revolution kind of decided secretly among themselves, literally that. We will put up one light at the top of a church if the British are coming by land, and we will instead use two if the British are instead coming by sea. Like, that is a code, and you could write it down in a book, and thus you have a code book. But of course, as soon as someone figures out that pattern, it's compromised. And so code books tend not to be the most robust mechanisms for encoding information. Instead, it's better to use something more algorithmic. And wonderfully, in computer science, is this black box, do we keep saying, the home of algorithms. And in general, encryption is a problem with inputs and outputs, but we just need one more input. The input is what's generally called a key or a secret. And a secret might just be a number. So for instance, if I wanted my secret to be 1, because we'll keep the example simple, but it could really be any number. And indeed, we saw with the photograph a moment ago, the Germans used much larger than this, albeit in the context of codes. Suppose that you now want to send a more private message to someone across the room in a class that I love you. How do you go about encoding that in a way that isn't just using ASCII and isn't just using some simple code book? Well, let me propose that now that we understand how strings are represented, right? We're about to make love really, really lame and geeky. So now that you know how to express strings computationally, well, let's just start representing I love you in ASCII. So I is 73, L is 76, O, V, E, Y, O, U. That's just ASCII. Should not send it this way, because anyone who knows ASCII is going to know what you're saying. But what if I enciphered this message? I performed an algorithm on it. And at its simplest sense, an algorithm can just be math, simple arithmetic, as we've seen. So, let me just use my secret key of 1. And let me make sure that my crush knows that I am using a secret value of 1. So he or she also knows to expect that value. And before I send my message, I'm going to add 1 to every letter. So 73 becomes 74, 76 becomes 77, 80, 87, 70, 90, 80, 86. Now, this could just be sent in the clear, but then I could actually send it as a textual message. So let's convert it back to ASCII. 74 is now J. 77 is now M. 80 is now P. And you can perhaps see the pattern. This message was I love you. And now all of the letters are off by 1, I think. I became J. L became M, O became P, and so forth. So now the claim would be, cryptographically, I'm going to send this message across the room. And now no one who has like a code book is going to be able to solve this. I can't just steal the book and decode it, because now the key is like only up here, so to speak. It's just the number 1 that he or she and I had to agree upon in advance that we would use for sending our secret messages. So if someone it captures this message, teacher in the room or whoever, how would they even go about decoding this or decrypting it? Are there any techniques available to them? I dare say we can kind of chip away at this love note. What's that? Guess and check. OK, we could try all. There's still kind of some spacing. So honestly, we could do like kind of a cryptanalysis of it, a frequency attack. Like, I can't think of too many words in English that have a single letter in them. So what does J probably represent? I, probably maybe A, but probably I, and there's not too many other options. So where we've attacked one part of the message already, I see a commonality. There's 2 what in here? 2P, and I don't necessarily know that that maps to O, but I do know it's the same character. So if I kind of continue this thoughtful process or this trial and error, and I figure out, oh, what if that's an O, and then that's an O, and then wait a minute, they're passing from one to another. Maybe this says I love you. Like, you actually can, with some probability, decrypt a message by doing this kind of analysis on it. It's at least more secure than the code book, because you're not compromised if the book itself is stolen, and you can change the key every time so long as you and the recipient actually agree on something. But at least we now have this mechanism in place. So with just the understanding of what you can do with strings, can you actually now do really interesting domain-specific things to them? And in fact, back in the day, Caesar, back in militaristic times, like, literally used a cipher quite like this. And frankly, when you're the first one to use these ciphers, they actually are kind of secure, even if they're relatively simple. But hopefully not just using a key of 1, maybe 2 or 13 or 25 or something larger. But this is an example of a substitution cipher or a rotational cipher, where like everything's kind of rotating. A is becoming B, B is becoming C, or you can kind of rotate it even further than that. Well, let's take a look at one last example here of just one other final primitive of a feature today, before we then go back high level to bring everything together. It turns out that printing out error messages is not the only way to signal that something has gone wrong. There's a new keyword, a new use of an old keyword in this example that's actually a convention for signaling errors. So this is an example called exit.c. It apparently wants the human to do what, if you infer from the code? Yes, say again? Well, what does it want the human to do implicitly based on the printfs here? How should I run this program? Yeah. Yeah, so for whatever reason, this program implicitly wants me to provide exactly 2 words at the prompt, because if I don't, it's going to yell at me missing command line argument, and then it's going to return 1, whatever that is. Otherwise, it's going to say hello such and such. So if I actually run this program, let me go back over here and do make exit, in my directory, make exit, OK, /exit, enter. I'm missing a command line argument. All right, let me put Zamila's name. Oh, hello, Zamila. Let me put Zamila Chan. Nope, missing command line argument. It just wants the 1. So in this case here. But it turns out I'm seeing visually the error message. But it turns out the computer is also signaling to me what the so-called exit code is. So long story short, we've already seen examples last week of how you can have a function return a value. And we saw how Erin came up on stage, and she returned to me a piece of paper with a string on it. But it turns out that main is a little special. If main returns a value, like 1 or 0, you can actually see that, albeit in a kind of a non-obvious way. If I run exit, and I run it correctly with Zamila as the name, if I then type echo $? Of all things, enter, I will then see exactly what main returned with, which in this case is 0. Now let me try and be uncooperative. If I actually run just /exit with no word, I see missing command line argument. But if I do the same cryptic command, echo $? I see that main exited with 1. Now, why is this useful? Well, as we start to write more complicated programs, it's going to be a convention to exit from main by returning a non-zero value if anything goes wrong. 0 happens to mean everything went well. And in fact, in all of the programs we've written thus far, if you don't mention return anything, main automatically and automatically for you returns 0. And it has been all this time. It's just a feature, so you don't have to bother typing it yourself. But what's nice about this, or what's real about this, is if on your Mac or PC, if you've ever gotten like an annoying error message that says error -29, a system error has occurred or something freezes, but you very often see numbers on the screen, maybe, like those error codes actually tend to map to these kinds of values. So when a human is writing software and something goes wrong and an error happens, they typically return a value like this, and the computer has access to it. And this isn't all that useful for the human running the program, but as your programs get more complex, we'll see that this is actually quite useful as a way of signaling that something indeed went wrong. Whew. OK, that's a lot of syntax wrapped in some loving context. Any questions before we look at one final domain? No? All right. So it turns out that we can answer the who cares question in yet another way too. It turns out, let me go ahead and open up an example of our array again here, that arrays can actually now be used to solve problems more algorithmically. And this is where life gets more interesting. Like, we were so incredibly in the weeds today, and as we move forward in the class, we're not going to spend so much time on like syntax and $ and question marks and square brackets and the like. Like, that's not the interesting part. The interesting part is when we now have these fundamental building blocks, like an array, with which we can solve problems. So it turns out that an array, you can kind of think of it as a series of lockers that might look like this, inside of which are values, strings or numbers or chars or whatnot. But the lockers is an apt metaphor because a computer, unlike us humans, can only see and do one thing at a time. It can open one locker and look inside, but it can't kind of take a step back like we humans can and look at all of the lockers, even if all of the doors are opened. It has to be a more deliberate act than that. So what are the actual implications? Well, all this time, we had that phone book example in the first week, and we were the efficiency of that algorithm of finding Mike Smith in this phone book all assumed what feature of this phone book? that it was ordered alphabetically. And that was a huge plus because then I could like go to the middle and I could go to the middle of the middle and so forth. And that was an algorithmic possibility. On our phones, if you pull up your contacts, you've got a list of first names or last names all alphabetically sorted. That is because guess what data structure or layout your phone probably uses to store your contacts? It's an array of some sort, right? It's just a list, and it might be displayed vertically instead of horizontally as I've been drawing it today. But it's just values that are back to back to back to back to back that are actually sorted. But how did they actually get into that sorted order, and how do you actually find values? Well, let's consider what this problem is actually like for a computer as follows. Let me go ahead here. Would a volunteer mind joining us up here? I can throw in a free stress ball. Maybe someone from back? OK, come on up here. Come on. What's your name? Aaron. All right. So Aaron's going to come on up. And I'm sorry? Oh, Eric. Nice to meet you. All right. Come on over here. So Eric, normally I would ask you to find the number 23. But seeing as that's a little easy, can you go ahead and just find us the number 50 behind these doors, or really these yellow lockers? 8? Nope. 42? Nope. OK. Pretty good. That's 3. 3 out of 7. So how would you get it so quickly?
I guessed.
OK. So he guessed. Is that the best algorithm that Eric could have used here? Well, I don't know. Yes? No? Why? Why yes? He has no other information. So yes, like that was the best you can do. But let me give you a little more information. You can stay here. And let me go ahead and reload the screen here. And let me go ahead and pull up a different set of doors. And now suppose that, much like the phone book and much like the phones are sorted, now these doors are sorted. And find us the number 50. All right, so good. What did you do that time?
Well, I checked the first one, and if it was 50 is 116, so just.
Right, so you jumped to the middle of to the middle initially, and then to the right half, and then technically, so we're technically off by 1, right? Because like binary search would have gone to the middle of the. That's OK, but very well done to Eric. Here, let me at least reinforce this with a stress ball. So thank you. Very well done. So with that additional information, as you know, like Eric was able to do better because the information was sorted on the screen. But he only had one insight to a locker at a time, because only by revealing what's inside can he actually see it. So this seems to suggest that once you do have this additional information in Eric's example, in your phone example, in the phone book example, like you open up possibilities for much, much, much more efficient algorithms. But to get there, we've kind of been deferring this whole time in class how you actually sort these elements. And if you wouldn't mind, and this way we'll hopefully end on a more energized note here, because I know we've been in the weeds for a while. Can we get like 8 volunteers? OK, so 1, 2, 3, 4, how about 5, 6, 7, 8? Come on down. Oh, I'm sorry. Did I completely overlook the front row? OK. All right, next time, next time. Come on down. Oh, and Colton, do you mind meeting them over there instead? All right, come on up. What's your name?
Kami.
Kami. David, right over there. What's your name? Matt. David. Juhei. David. Max. Nice to meet you. James. Nice to see you. Here, I'll get more chairs. What's your name? Peyton. David. And 2 more. Actually, can one of you come down to this end here? What's your name?
I'm Andrea.
Andrea. Nice to see you. And your name?
Hi,
Pico. David. Nice to see you. OK. Colton has a T-shirt for each of you. Very Harvard-esque here. And each of these shirts, as you're about to see, has a number on it. And that number is I'll go ahead and put them on if you wouldn't mind. OK, thank you so much. So I dare say we've arranged our humans, much like the lockers, in an array. Like we have humans back to back to back to back. But this is actually both a blessing and a constraint, because we only have 8 chairs. So there's really not much room here. So we're confined to just this space here. And I see we have a 4, 8, 5, 2, 3, 1, 6, 7. So this is great. Like they are unsorted by definition. It's pretty random. So that's great. So let's just start off by this. Sort yourselves from 1 to 8, please. OK. All right. Well, what algorithm was that? Look around, figure it out. OK. Well, human ingenuity. Very well done. So can we? What was like a thought going through any of your minds? Find the chair, or find the right chair. So go to the go-to location. Good. So like an index location, right? Arrays have indices, so to speak, 0, 1, 2, all the way up to 7. And even though our shirts are numbered from 1 to 8, you can think in terms of 0 to 7. So that was good. Anyone else? Other thoughts?
Yeah, I mean, this is something we implicitly think of, but no one told us that it was ordered right to left. Like, we could have done it left to right.
OK, absolutely. Could have gone from right to left instead of left to right. But at least we all agreed on this convention, too. So that was in your mind. OK, so good. So we got this sorted. Go ahead and re-randomize yourself if you could. And what algorithm was this? Just random awkwardness. OK, so that's fine. So it looks pretty random. That'll do. Let's see if we can now reduce the process of sorting to something a little more algorithmic so that, one, we can be sure we're correct and not just kind of get lucky that everyone kind of figured it out and no one was left out. And two, then start to think about how efficient it is, right? Because if we've been gaining so much efficiency for the phone book, for our context, for Eric coming up, like we really should have been asking the whole time, sure, you save time with binary search and divide and conquer, but how much did it cost you to get to a point where you can use binary search and divide and conquer? Because sorting, if it's super, super, super expensive and time consuming, maybe it's a net negative, and you might as well just search the whole list rather than ever sort anything. All right, so let's see here. 6 and 5. I don't like this. Why? 6 supposed to come after 5. And so can we fix this, please? All right, and then let's see. OK, 6 and 1. Don't really like this. Can we fix this? Very nice. 6 and 3. OK, you really got the short end of the stick here. So 6 and 3. Could we fix this? And 6. Yeah, OK. OK. 6 and 7. Good. All right. So that's pretty good. 7 and 8. Nice. 8 and 4. Sorry. Could we switch here? All right. And then 8 and 2. OK. Could we switch here? OK. And let me ask a somewhat rhetorical question. OK. Am I done? OK, no, obviously not. But I did fix some problems, right? I fixed some transpositions, numbers being out of order. And in fact, what's your name again?
Kami.
Kami kind of bubbled to the right here, if you will. Like you were kind of farther down, and now you're over here. And like the smaller numbers kind of, yeah, 1, like, my God, like he kind of bubbled his way this way. So like things are percolating in some sense, and that's a good thing. And so, let me try to fix some remaining problems. So 1 and 5, good. Oh, 3 and 5, could you switch? 5 and 6. OK, 6 and 7. 7 and 4, could you switch? OK. And 7 and 2, could you switch? And now I don't have to speak with Kami again because we know you're in the right place. So I actually don't have to do quite as much work this time, which is kind of nice. But am I done? Like, no, obviously not. But what's the pattern now? Like, what's the fundamental primitive? If I just compare pairwise humans and numbers, I can slightly improve the situation each time by just swapping them. And each time, now, I'm sorry, Pico is in number 7's place. I don't have to talk to him anymore because he's now bubbled his way all the way up to the top. So even though I'm doing the same thing again and again, and looping again and again isn't always the best thing, so long as you're looping fewer and fewer times, I will eventually stop, it would seem, because 6 is going to eventually go in the right place, and then 5, and then 4, and so forth. So if we can just finish this algorithm, good, 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 not good. OK, 6 and 2, not good. If you could swap. OK, what's your name again? Peyton. Peyton is now in the right place. I have even less work now ahead of me. So if I can just continue this process, 1 and 3, 3 and 5, 4 and 5. OK, and then 2 and 5. And then what's your name again? Matt is now in the right place. Even less work. We're almost there. 1 and 3, 3 and 4, 4 and 2. If you could swap. OK, almost done. And 1 and 3, 3 and 2. If you could swap. Nice. So this is interesting. It would seem that, in the first place, I kind of compared 7 pairs of people. And then the next time I went through, I compared how many pairs of people maximally. Just 6, right? Because we were able to leave Kami out, and then we were able to leave Pico out, and then Peyton. And so the number of comparisons I was doing was getting fewer and fewer. So that feels pretty good. But you know what? Before we even analyze that, can you just randomize yourselves again? Any human algorithm is fine. Let's try one other approach, because this feels kind of non-obvious, right? I was fixing things, but I had to keep fixing things again and again. Let me try to take a bigger bite out of the problem this time by just selecting the smallest person. OK, so your name again is? Juhei. Number 2, that's a pretty small number, so I'm going to remember that in sort of a mental variable. 4, no, you're too big, too big, too big, too big. Oh, what was your name again? James. James is a 1. That's pretty nice. Let me keep checking. OK, James in my mental variable is the smallest number. I know I want him at the beginning, so if you wouldn't mind coming with me. And I'm sorry, we don't have room for you anymore. If you could just, oh, you know what? Could you all just shuffle down? Well, I don't know if I like that. That's a lot of work, right? Moving all these values. Let's not do that. Let's not do that. Number 2, could you mind just going where James was? OK. So I've kind of made the problem a little worse, and that now number 2 is farther away from the goal. But I could have gotten lucky, and maybe she was number 7 or 8. And so let me just claim that on average, just evicting the person is going to kind of be a wash and average out. But now James is in the right place. Done. Now I have a problem that's of size 7. So let me select the next smallest person. 4 is the next smallest, not 8, not 5, not 7. Ooh, 2, not 3, 6. OK, so you're back in the game. All right, come on back. And can we evict number 4? And on this algorithm, if you will, I just iteratively select the smallest person. I'm not comparing everyone in quite the same way and swapping them pairwise. I'm doing kind of more macroscopic swaps. So now I'm going to look for the next smallest, which is 3, if you wouldn't mind popping it on here. Kami, we have to unfortunately evict you, but that works out to our favor. Let me look for the next smallest, which is 4. OK, you're back in. Come on down. Swap with 5. OK, now I'm looking for 5. Hey, 5, there you are. OK, so go here. OK, looking for 6. Oh, 6, a little bit of a shuffle. OK, and now looking for 7. Oh, 7, if you could go here. But notice I'm not going back. And this is what's important. Like my steps are getting shorter and shorter. My remaining steps are getting shorter and shorter. And now we've actually sorted all of these humans. So 2 fundamentally different ways, but they're both comparative in nature because I'm comparing these characters again and again and again and swapping them if they're out of order. Or I'm at a higher level going through and swapping them again and again and again. But how many steps am I taking each time? Even though I was doing fewer and fewer and I wasn't doubling back, the first time I was doing like n-1 comparisons. And then I went back here. And in the first algorithm, I kind of stopped going as far. In the second algorithm, I just didn't go back as far. So it was just kind of a different way of thinking of the problem. But then I did, what, like 7 comparisons, then 6, then 5, then 4, then 3, then 2, then 1. It's getting smaller. But how many comparisons is that total? If I've got like n people, n being a number, it's not as bad as factorial. We'd be here all day long. But it is big. It is big. Let's a round of applause if we could for our volunteers. You can keep the shirts if you'd like as souvenir. Thank you very much. Let me see if we can't just kind of quantify that. Thank you so much. And see how we actually got to that point. If I go ahead and pull up, not our lockers, but our answers here, let me propose that what we just did was essentially 2 algorithms. One has a name bubble, and I was kind of deliberately kind of shoehorning the word in there. Bubble sort is just that comparative sort, pair by pair, fixing tiny little mistakes. But we needed to do it again and again and again. So those steps kind of add up, but we can express them as pseudocode. So in pseudocode, and you can write this any number of ways, I might just do the following. Just keep doing the following until there's no remaining swaps. From 0 to n-2, which is just n is the total number of humans. n-2 is go up from that person to this person, because I want to compare him or her against the person next to them. So I don't want to accidentally do this. That's why it's n-2 at the end here. Then I want to go ahead and if the ith and the ith plus 1 elements are out of order, swap them. So that's why I was asking our human volunteers to exchange places. And then just keep doing that until there's no one left to swap. And by definition, everyone is in order. Meanwhile, the second algorithm has a conventional name of selection sort. Selection sort is literally just that, where you actually select the smallest person or number of interest to you iteratively again and again. And the number keeps getting bigger, but you start ignoring the people who you've already put into place. So the problem, similarly, is getting smaller and smaller. Just like in bubble sort, it was getting more and more sorted. The pseudocode for selection sort might look like this. For I from 0 to n-1, so that's 0 in an array, and this is n-1, just keep looking for the smallest element between those 2 chairs, and then pull that person out, and then just evict whoever's there. Swap them, but not necessarily adjacently, just as far away as is necessary. And in this way, I keep turning my back on more and more people because they are then in place. So 2 different framings of the problem, but it turns out they're actually both the same number of steps, give or take. It turns out they're roughly the same number of steps, even though it's a different way of thinking about it. Because if I think about bubble sort, the first iteration, for instance, let's consider selection sort even. In selection sort, how many comparisons did I have to do? Well, once I found my smallest element, I had to compare them against everyone else. So that's n-1 comparisons the first time. So n-1 on the board. Then I can ignore them because they're behind me now. So now I have how many comparisons left out of n people? n minus 2, because I subtracted 1, then again n minus 3, then n minus 4, all the way down to just one person remaining. So I'll express that sort of generally mathematically like this. So n minus 1 plus n minus 2 plus whatever plus one final comparison, whatever that is. It turns out that if you actually read the back of the math book or your physics textbooks where they have those little cheat sheets as to what these recurrences are, turns out that n minus 1 plus n minus 2 plus n minus 3 and so forth can be expressed more succinctly as literally just n times n minus 1 divided by 2. And if you don't recall that, that's OK. I always look these things up as well. But that's true, fact. So what does that equal out to? Well, that's like n squared minus n if you just multiply it out. And then if you divide the 2, then it's n squared divided by 2 minus n over 2. So that's the total number of steps. And I could actually plug this in. We could plug in 8, do the math, and get the total number of comparisons that I was verbally kind of rattling off. So is that a big deal? It feels like it's on the order of n squared. And indeed, a computer scientist, when assessing the efficiency of an algorithm, tends not to care too much about like the precise values. All we're going to care about is like the biggest term. What's the value in the formula that you come up with that just dominates the other terms, so to speak, that has the biggest effect, especially as n is getting larger and larger. Now, why is this? Well, let's just do sort of proof by example, if you will. If this is the expression, technically, but I claim that it's close enough to say on the order of, big O of n squared, so to speak. Let's use an example. If there's 1 million people on stage and not just 8, that math works out to be like 1 million squared divided by 2 steps minus 1 million divided by 2 total. So what does that actually work out to be? Well, that's 500 billion minus 500,000. And what does that work out to be? Well, that's 499 billion, 999,500,000. That feels pretty darn close to like n squared. I mean, that's a drop in the bucket to subtract 500,000 from 500 billion. So you know what? It's on the order of n squared. It's not precise, but it's in that general order of magnitude, so to speak. And so this symbol, this capital O, is literally a symbol used in computer science and in programming to just kind of describe with a wave of the hand, but some good intuition in algorithm, how fast or slow your algorithm is. And it turns out there's different ways to evaluate algorithms with just different similar formulas. N squared happens to be how much time both bubble sort and selection sort take. If I literally count up all of the work we were doing on stage with our volunteers, it would be roughly n squared, 8 squared, or 64 steps, give or take, for all of those humans. And that would be notably off. There's a good amount of rounding error there. But if we had 1 million volunteers on stage, then the rounding error would be pretty negligible. But we've actually seen some of these other orders of magnitude, so to speak, before. For instance, when we counted someone or we searched for Mike Smith 1 page at a time, we called that a linear algorithm. And that was big O of n. So it's on the order of n steps. It's 1,000, maybe it's 999, whatever. It's on the order of n steps. The twosies approach was twice as fast, recall, 2 pages at a time. But you know what? That's still linear, right? Like 2 pages at a time. Let me just wait till next year when my CPU is twice as fast because Intel and companies keep speeding up computers. The algorithm is fundamentally the same. And indeed, if you think back to the picture we drew, the shapes of those curves were indeed the same. That first algorithm, finding Mike 1 page at a time, looked like this. Second algorithm, finding him, looked like this. Only the third algorithm, the divide and conquer, splitting the phone book, was a fundamentally different shape. And so even though we didn't use this fancy phrasing a couple weeks ago, these first 2 algorithms, 1 page at a time, 2 pages at a time, they're on the order of n. Technically, yes, n versus n divided by 2. But we only care about the dominating factor, the variable, n. We can throw away everything in the denominator, and we can throw away everything that's smaller than the biggest term, which in this case is just n. And I alluded to this 2 weeks ago. Logarithmic, well, it turns out that anytime you divide something again and again and again, you're leveraging a logarithmic type function, log base 2 technically. But on the order of log base n is a common one as well. The beautiful algorithms are these. Literally 1 step, or technically constant number of steps. For instance, like what's an algorithm that might be constant time? Open phone book. OK, 1 step. Doesn't really matter how many pages there are. I'm just going to open the phone book, and that doesn't vary by number of pages. That might be a constant time algorithm, for instance. So those are the lowest you can go. And then there's somewhere even in between here that we might aspire to with certain other algorithms. So in fact, let's just see if just a moment. Let's just see if we can do this a little more succinctly. Let's go ahead and use arrays in just one final way using merge sort. So it turns out using an array, we can actually do something pretty powerfully, so long as we allow ourselves a couple of arrays. So again, when we just did sorting with bubble sort and selection sort, we had just one array. We had 8 chairs per people, for our 8 people. But if I actually allowed myself like 16 chairs or even more, and I allowed these folks to move a bit more, I could actually do even better than that using arrays. So here's some random numbers that we'll just do visually without any humans. And they're in an array, back to back to back to back. But if I allow myself a second array, I'm going to be able to shuffle these things around and not just compare them, because it was those comparisons and all of my footsteps in front of them that really started to take a lot of time. So here's my array. You know what? Just like the phone book, that phone book example got us pretty far in the first week. Let me do half of the problem at a time and then kind of combine my answers. So here's an array, 4, 2, 7, 5, 6, 8, 3, 1, randomly sorted. Let me go ahead and sort just half of this, just like I searched for Mike initially and just half of the phone book. So 4, 2, 7, 5, not sorted. But you know what? This feels like too big of a problem still. Let me sort just the left half of the left half. OK, now it's a smaller problem. You know what? 4 and 2, still out of order. Let me just divide this list of 2 into 2 tiny arrays, each of size 1. So here's a mini array of size 1, and then another one of like size 7, but they're back to back, so whatever. But this array of size 1, is it sorted? Sorry? No? If this array has just one element, and that element is 4, yes, then it is sorted by definition. All right, so done. Making some progress. Now let me kind of mentally rewind. Let me sort the right half of that array. So now I have another array of size 1. Is this array sorted? Yeah, kind of stupidly. We don't really seem to be doing anything. We're just making claims. But yes, this is sorted. But now this was the original half. And this half is sorted. This half is sorted. What if I now just kind of merge these sorted halves? I've got 2 lists of size 1, 4 and 2. And now if I have extra storage space, if I had like extra benches, I could do this a little better. Why don't I go ahead and merge these 2 as follows? 2 will go there. 4 will go there. So now I've taken 2 sorted lists and made one bigger, more sorted list by just merging them together, leveraging some additional space. Now let me mentally rewind. How did I get to 4 and 2? Well, I started with the left half, then the left half of the left half. Let me now do the right half of the left half, if you will. All right, let me divide this again. 7, a list of size 1. Is it sorted? Yes, trivially. 5, is it sorted? Yes. 7 and 5, let's go ahead and merge them together. 5 is, of course, going to go here. 7, of course, is going to go here. OK. Now, where do we go? We originally sorted the left half. Let's go to sort the right. Oh, right, sorry. Now, we have the left half and the right half of the left half are sorted. Let's go ahead and merge these. We have 2 lists now of size 2, 2, 4, and 5, 7, both of which are sorted. If I now merge 2, 4 and 5, 7, which element should come first in the new longer list, obviously? 2, and then 4, and 5, and then 7. That wasn't much of anything. But OK, we're just using a little more space in our array. Now what comes next? Now let's do the right half. Again, we started by taking the whole problem, doing the left half of the left half, the left half of the left half of the left half. And now we're going back in time, if you will. So let's divide this into 2 halves. Now the left half into 2 halves still. 6 is sorted. 8 is sorted. Now I have to merge them. 6, 8. What comes next? Right half. 3 and 1. Well, left half is sorted. Right half is sorted. 1 and 3. All right, now how do I merge these? 6, 8, 1, 3. Which element should obviously come first? 1, then 3, then 6, then 8. And then lastly, I have 2 lists of size 4. Let me give myself a little more space, one more array. Now let me go ahead and put 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8. What just happened? Because it actually happened a lot faster, even though we were doing this all verbally. Well, notice how many times did each number change locations? 4, well, literally 3, right? Like 1, 2, 3, right? It moved from the original array to the secondary array to the tertiary array to the fourth array, whatever that's called. And then it was ultimately in place. So each number had to move 1, 2, 3 spots. And then how many numbers are there? Well, they were already in the original array. So how many times did they have to move? Just 1, 2, 3. So how many total numbers are there, just to be clear? There's 8. So 8 times 3. So let's generalize this. If there's n numbers, and each time we moved the numbers, we did like half of them, then half, then half. Well, how many times can you divide 8 by 2? 8 goes to 4, 4 goes to 2, 2 goes to 1. And that's why we bottomed out at 1 element, lists of size 1. So it turns out whenever you divide something by half, by half, by half, what is that function or formula? Not power, that's bad. That's the other direction. It's a logarithm. So again, logarithm is just a mathematical description for any function that you keep dividing something again and again and again, in half and half and half, in third and third and third, whatever it is. It just means division by the same proportional amount again and again and again. And so if we move the numbers 3 times, or more generally, log of n times, which again just means you divided n things again and again and again, you just call that log n. And there's n numbers. So n numbers moved log n times. The total arithmetic here in question is one of those other values on our little cheat sheet, which looked like this. In our other cheat sheet, recall that we had formulas that looked like this, not just n squared and log n and 1. We had this one in the middle, n times log n. So again, we're kind of jumping around here. But again, each number moved log n places. There's n total numbers. So n times log n is just, by definition, n log n. But why is this sorted this way? Well, log n, recall from week 0 with the phone book example, the green curve is definitely smaller than n. N was the straight lines. Log n was the green curved one. So this indeed belongs in between, because this is n times n. This is n. This is n times something smaller than n. So what's the actual implication? Well, if we were to run these algorithms side by side and actually compare them with something like this, let me go ahead and compare these algorithms using this demo here. If I go ahead and hit play, we'll see that the bars in this chart are actually horizontal, and the small bars represent small numbers, large bars represent long numbers, and then each of these is going to run a different algorithm. Selection sort on the left, bubble sort in the middle, merge sort, as we'll now call it, on the right. And here's how long each of them take to sort those values. Done. Bubble's still going, selection's still going. And so that's the appreciable difference, albeit with a small demo, between n squared and something like log n. And so what have we done here? We really got into the weeds of what arrays can actually do for us and what the relationships are with strings, because all of it kind of reduces to just things being back to back to back to back. But now that we kind of come back, and we'll continue along this trajectory next time, we're able to talk at a much higher level about what's actually going on. And we can now take this even further by applying other sort of forms of media to these same kinds of questions. And we'll conclude it's about 60 seconds long. These bars are vertical instead of horizontal. And what you'll see here is a visualization of various sorting algorithms, among them selection sort, bubble sort, and merge sort, and a whole assortment of others, each of which has even a different sound to it because of the speed and the pattern by which it actually operates. So let's take a quick look. This is bubble sort. And you can see how the larger elements are indeed bubbling up to the top. You can kind of hear the periodicity or the cycle that it's going in. And there's less and less and less and less work to do until almost. This is selection sort now. So it starts off random, but we keep selecting the smallest human, or in this case, the shortest bar. And you'll see here the bars correlate with frequency clearly. So it's getting higher and higher and taller and taller. This is merge sort now, which, recall, does things in halves, and then halves of halves, and then merges those halves. So we just did all the left work, almost all of the right work. That one's very gratifying. This is something called GNOME sort, which is improving things, not quite perfectly, but it's always making forward progress and then kind of doubling back and cleaning things up. That was a lot. Let's call it a day. I'll stick around for one-on-one questions. We'll see you next time. Okay.